ID the Future, a podcast about evolution and intelligent design.
Welcome to ID the Future. I'm Eric Anderson, and we're joined again today by Dr. Robert Stadler to continue discussing the importance of energy harnessing in the origin of life. Stadler has degrees in biomedical engineering, electrical engineering, and medical engineering. He is also co-author of the recent book, The Stairway to Life, An Origin of Life Reality Check. Thanks for being back with us, Rob.
Hi, Eric. Good to be here. Thank you.
So last time we were talking about a wonderful new video in the series Long Story Short on the Discovery Science YouTube channel that you've had an opportunity to be involved with, along with a number of other scientists. And we were talking about this remarkable system, ATP synthase, and how that machine works with the proton gradient across the membrane and everything that was going on with that. And at the end, Rob, you were talking about an alternative approach to producing a small amount of ATP, which is fermentation. Remind us just a little bit about that, and then I'd like to ask a follow-up question to that.
Yeah, so the bigger process that almost all of life uses first produces a proton gradient across the membrane, and then it uses ATP synthase to convert that proton gradient into ATP, kind of like charging up batteries. And then finally, those batteries get used to do all of the activities of keeping life going, basically the building of molecules and replicating and maintaining and repairing and transportation and homeostasis and all of the above.
Mm-hmm.
So fermenters are sometimes considered a shortcut to that, if you will, because they can generate ATP directly through a chemical reaction called substrate level phosphorylation.
Okay.
And so they don't need the ATP synthase for that purpose. But as we mentioned last time, it's very interesting that they still actually have to have ATP synthase, and they actually run it in the reverse direction, where they burn ATP in order to create and maintain the proton gradient.
Interesting.
Because that proton gradient is also required for transportation across the membrane,
right,
which is required for them to stay alive. So fermenters then seem to be a degenerate form of life that are very sensitive to the type of food they can survive on. And they also require other forms of life to be around to kind of clean up the mess they've made and keep them going.
Right. I know that Craig Venter's group was working on a simple form of life, trying to reduce an organism to the minimum amount required. I think that was a fermenter.
Yeah, so that fancy name of JVCI Syn3A sounds like a pretty fancy form of life. Yeah, of course, it's a simplified form of life where it's like a boat where they've cast out everything they can throw overboard, just barely enough to keep the thing floating. And so, it is it's a fermenter. It's an obligate fermenter. It can only derive energy from glucose, its only energy source being glucose, and it only does its fermentation reaction to directly produce ATP, which it needs to survive. So humans must be there to continually provide it with the right kind of food, and also to clean up the waste of its reaction, or else that would end up poisoning it and stopping any growth.
Interesting.
So
instead of other bacteria or other forms of life cleaning up the waste product, the human's actually doing that as part of the experiment. Yeah.
That's how it's used in the lab. Yeah. And so it is a fermenter, and as I said, it does have to run its ATP synthase in reverse.
Mm-hmm.
So you could call it, the simplest form of life that we're aware of right now. But simplifying it down that far has a very important central theme, in that it becomes very fragile. It becomes required. It has requirements to be coddled and to have all of the right nutrients, especially glucose, supplied to it at just in the right concentration at the right time, and to have someone clean up its waste for it.
Yeah, and it still requires a membrane that's specialized. It still requires ATP synthase. It still requires proton gradient. The things you outlined last time as being essentially required. Seems like we're not getting away from those.
Yeah, and of course, to remember that it's over 500,000 base pairs of DNA and about 400 genes. And so, yes, it is the simplest form of life we're aware of that can survive, but it's certainly very complex and certainly very fragile.
Yeah, yeah. Now, what about some of those other forms we've heard of, like methanogens and cetogens? Tell us about those.
Yeah, so sometimes when people are trying to point to simpler forms of life that can sort of sidestep the complexity of energy harnessing, sometimes they'll point to methanogens and acetogens, which are bacteria and archaea who they basically produce methane or acetone, and they do it through basically a different process of producing the proton gradient. They do have the proton gradient. They have to produce it in order to make ATP.
Okay.
But they use what's called the acetyl-CoA pathway to produce the proton gradient instead of what normal life does, which are the respiratory complexes of life. Very complex. We have those. And they still need ATP synthase then to use that proton gradient to generate their ATP. So most of the whole process, which we gave the fancy name of chemiosmotic coupling, almost all of that process is still maintained in these methanogens and acetogens, but they do have a different path to producing the proton gradient, which is this acetyl-CoA pathway.
Okay, as opposed to the electron transport chain, you're saying.
That's right, exactly. Now, what they do to produce their source of food is kind of unique, and they use hydrogen gas and carbon dioxide. And in combining those to extract a little bit of energy from that process, and that's, in the end, they produce methane from it. That as a food source doesn't produce a lot of food. It doesn't produce a lot of energy.
Mm-hmm.
You get a little bit of energy from that. And that reaction on its own is not enough energy to make ADP into ATP.
Okay.
And so they have to extract that small amount of energy through the acetyl-CoA pathway to create a little bit of a proton gradient. And as we mentioned in the last discussion we had, it's a little bit like a hydroelectric dam where you're building up water above the dam through this, it would be like the analogy of the proton gradient of having water built up behind the dam. So reacting hydrogen gas and CO2 just gives you a few drips of water that you can slowly over time build up water behind that dam and then use that to build ATP through ATP synthase.
Yeah. But does the acetyl-CoA pathway also require some specialized enzymes?
Exactly. Yeah. So I guess you could argue that it's a little simpler than the respiratory complexes, but it's still a rather complex pathway to build up that proton gradient.
Okay. So at the end of the day, we've got an alternate way of building up the proton gradient, but we're still using ATP synthase, and we still have machinery that's required to build up that gradient.
Yeah, and it's as you've indicated, it's very far from simple.
Yeah. Okay. So let's talk about that, though. There must surely be, Rob, if life evolved on the early Earth through unguided processes, surely there must have been something simpler. We just need to keep looking harder, and eventually we'll find some simpler way to harness energy than what we see in biology.
Yeah, and that is the sort of rebuttal that we hear the most. It's kind of convenient in a way because it's kind of a rebuttal from imagination, and whatever.
Yeah. Yeah, I'm going to use that term. I like that.
Yeah, rebuttal from imagination. And it's also very convenient that they can say, well, this has happened so long ago that all the evidence is gone. There really isn't.
The haziness of time has scared the evidence, right?
So there's no evidence, but you can imagine it's possible. And that's about as strong as the argument gets.
Why do you think it's a poor approach, though? I mean, setting aside that it's a poor argument, we know from a standpoint of evidence, a standpoint of how these systems have to work. Why do you think it's a poor approach?
Yeah, and I think, you can take the bottom-up argument, which is to say, it's kind of how we started this conversation last time, is to say that we know there are raw forms of energy on the prebiotic Earth, like lightning or volcanoes or radiation, the sun. But it's clear that those raw forms of energy will not predominantly be constructive. They will predominantly, as far as chemical reactions go or building complex biomolecules, they're going to be predominantly destructive. And so you can't just rely on luck and raw energy to build this up. There must be something more sophisticated than that. And then we can take the top-down approach, which we've done here with like Craig Venter's simplified cell, and recognize that existing life has a complicated process, but it's complicated because it has to be, because that provides a robustness to life. It provides life with the ability to survive off different kinds of energy in different circumstances. It's kind of like a entrepreneurial 10-year-old who is able to make some money by cutting grass and by babysitting and by chores, washing the dishes. And and you can make money in little different ways, and you can build that up into a savings account and then make a big purchase. That's kind of the robustness that life needs in order to survive. Whereas if you degenerate it down in a way like fermenters do, you're left with being very sensitive to one kind of energy source that has to be supplied just at the right time. So if you go back to the big argument that our people who rebut this make, that it had to start simpler. Unfortunately, starting simpler just means that it's going to be very fragile and have to be just coddled in just the right way in order to make progress and not die and end the whole process of progress that it's made.
Yeah, and if you have a simpler organism, then it's more dependent upon its environment to provide exactly what it needs at the right time and in the right way. So there's this, I think a lot of people who are proponents of abiogenesis misunderstand this point, because there's this very simplistic and naive idea that back on the early Earth, it would have been easier for life to start. It would have been simple, because Darwin talks about that, Dawkins talks about that. It's sort of assumed in origin of life research today. But if you have nothing but a barren environment, then your first life form has got to be pretty capable, because it's not getting, like in the case of Venter's JCVI SYN 3.0, it's not getting glucose provided conveniently by the environment.
Yeah, exactly.
And so there's this disconnect. The environment provides certain things, the organism's going to do certain things. There's an inverse ratio, I guess is what I'm talking about, an inverse relationship between how much coddling the environment does and how much the organism has to do on its own. And on the early Earth, it actually would have been an incredibly difficult place.
Yeah, it's frankly hard to imagine that any type of life could make it completely on its own with no other life helping it out or forming a sort of ecology. Such a form of life, to get it started, would have to be a kind of like a Swiss Army knife of life that can pull out all kinds of tools to get through any kind of change in the environment, any kind of challenge that it faces. And of course, that means it would have to be extremely complex from the beginning, and not as envisioned, not as a very simple beginning. That doesn't make sense to me.
Yeah, that's a really important point. So, Rob, let me just have you address a couple of the criticisms from some of the viewers of the video, and maybe you can help us with these so that we understand the responses. One was that there's this fungus that grows off of the radiation at Chernobyl. So the argument is there's different ways to gain energy and to grow rather than using ATP synthase. What's your response to that?
Yeah, that's kind of a fascinating story that they found inside the reactor at Chernobyl. There's a fungus growing that's apparently surviving off of the radiation. Very fascinating story. I would first note that a fungus is eukaryotic, so it's a very complex form of life. It's certainly not leading you to think that very, very simple life could have developed a new way of harnessing energy like that. And so it turns out they don't know exactly yet how this fungus is surviving, but I think we can make a pretty strong prediction that it'll be a chemiosmotic approach, just like all eukaryotes use, and it'll be somehow related to photosynthesis, something close to that, but it's going to be quite complex and not a sort of a shortcut pathway to harnessing energy.
Yeah, and I think you can say probably that it's going to require, as the real point of the video was, that you have to have a way to harness this energy and put it into usable form for the cell. And you can't just throw an organism in a radiation situation and expect good to come of it. If you've got the equipment and the machinery within the cell to take advantage of it, then yes.
Yep. There was even talk of growing this fungus on purpose out in the International Space Station or on any spaceship to protect the astronauts from radiation. It's kind of
right. Okay. Interesting. I hadn't heard that. That's great.
Interesting concept.
So just one last criticism, Rob, and this is kind of a devil's advocate thing here. You're saying that life has these certain machines that are required in certain processes, that are required to harness this raw energy targeted to a usable form for the cell. But isn't this sort of a God of the gaps argument? We don't know how it could have happened early on the Earth, so we're just assuming that it must have been complicated like it is today in biology.
Yeah, we certainly hear the God of the gaps rebuttal a lot, that we've encountered something very complex. We don't know how it got there, therefore God must have done it. I think through the discussion we've had here, we're making it clear that we know a lot about life. We know a lot about how it works and what is required to harness energy to keep it running.
Mm.
And the requirements for energy harnessing do not have any valid shortcuts that could reduce it by 50%, 80%, 90% down to something extremely simple that's still viable. And so we're not attempting to fill a gap with God. We're basically saying that we know enough to know that natural processes on their own could not have gotten us to where we're at now. From a prebiotic Earth to what is required to keep something alive, we know enough to know that natural processes can't do that. So if you maintain a belief that natural processes did do that, to me, that's very much the opposite, what I would call naturalism of the gaps, to believe that that's true, because it goes against what we understand about nature and about science.
Right. So the argument that you're making is based on what we do know and the best science that we do have and the best evidence we do have, whereas the opposite is sort of saying, well, gee, I'm going to ignore all that and just pretend that maybe someday something else will pop up that will support my position.
Yes, maybe some new law of physics will be discovered.
Oh, boy. Oh, we should have you back to talk about that. That's one of my favorite topics as well, and it's becoming very popular. Well, Rob, thank you so much for being with us to help us talk through this remarkable need to harness energy and to use it in the right way so that cells can grow and we can be here alive talking to each other on this channel. Thanks so much for being with us, Rob.
Yeah, thank you very much, Eric, and keep making ATP for us.
You too. Thank you for listening to this episode of ID the Future. To learn more about the origin of life, visit us at our YouTube Discovery Science channel at idthefuture.com or on your favorite podcast app. And as always, consider sharing a link with a friend. For ID the Future, I'm Eric Anderson. Thanks for listening.
Visit us at idthefuture.com and intelligentdesign.org. This program is copyright Discovery Institute and recorded by its Center for Science and Culture.